Welcome back to part 2 of calculator linking in assembler. Last time we talked about the hardware layer. This time I'm going to continue a bit in the hardware layer because I forgot a tiny bit, and then we're going to continue on the byte layer. First, the physical layer. The thing I forgot last time is that we ended on this table, right? And this table contains everything you need to know to be able to use it. But there's one thing that I forgot, and that's how to make it useful. And for one example on how to make it useful, I'm going to show you the Bell library. The Bell library, you can download it on bell.tremendous.com. You click on download. Let's say pick the newest version. You open the zip file and you open the include file. Now, once you open the include file, you scroll down to this part. Select proper hardware settings. In this part, I try to figure out what calculator you're assembling for, and then depending on that calculator, I set some values. Okay, so now we got those values from that table in our assembly file. We're going to go one step further. We're going to abstract things away a bit more, because we just want to be able to tell the assembler, please set both lines low. And we wanted to do it. We don't want to have to think about that. So that's what this code does. These are 4 defines: set high high, set low low, set low high, and set high low. And these 4 defines are structured in such a way that if you put this in your code, then it will be swapped out for this and then followed by this on a new line. So if we say set high high, then what happens is the right base value is loaded in A and it's sent out port 0. In other words, both lines are reset to the default values of high high, because the right base value, as I shown last time in the table, means that both are high, unless you set a bit on that value. Now that's what we're going to do now. So if we take a look at set low high, what it does is set the tip low and leave the ring high, as stated here. So we take the right base value again, but we have to set a bit. Now, so what we do is we take 1 and we shift it left, right tip bit times, and we all the right base value with that new value. But then we send it out port 0 again. So I'm assuming you all know what shifting does and all that. What is interesting to mention here is that obviously you can only do these things if your assembler understands that. If your assembler can't shift values around and can't define values in this way, then you need to do it a bit more low-level version. But this is the way that I did it in Ben Rives assembler, Brass, I think it's called, yes, Brass, and that works wonders for me. So that's writing. Reading from the port is, I have done it twice actually. Here's the read tip thing. All that does is load in a value from port 0 in A, and then check the read tip bit, whichever bit that is, as has just been defined depending on your platform. And the read ring function, not really function of course, does the same thing, only it reads the ring bit. Now the more complex version is this Bell read lines thing. If you call read lines, then you get a value back in A, and that value corresponds to one of these possible options. Okay, so that really concludes the physical layer, the first layer in our network stack. Because now we have all the functions and all the defines and everything we need to be able to set the lines, reset the lines, and also read the lines. And we can use that in our layers that we're going to build on top of this. So we're going to use this layer as the foundation for the rest. So if I go back to the presentation, we're now going to continue on the byte layer. We can do all that stuff, but how are we going to form bytes with it? There's 2 general schools of thought on this. The first being a serial protocol, and the second being a clocked protocol that's used in parallel communications. The serial version that I'm going to discuss first is used in Texas Instruments operating system, for example, and as you can see, this is the tip line and this is the ring line. The tip here is being pulled low at some point. That represents a 0. If we pull the ring low, that represents a 1, right? So what the other calculator, receiving calculator, does is it pulls the other line low. So if here the tip is being pulled low, then calculator B will pull the ring low. Calculator A will know, right, it's been read, I can now release my line, and I can pull the next. So the next one is a ring being pulled low. Calculator B acknowledges that with a tip being pulled low, so that is this part. And then the final bit is that calculator A pulls the ring low again, so it's another 1, and calculator B acknowledges that with another tip ring being pulled low, so that's an acknowledge. So that's a fairly simple system. It has 2 advantages. First, it's very robust because every bit is being acknowledged. You can hardly make a mistake in there. Every bit has to be correct. And second, it's compatible with the Texas Instruments operating system, so that's another advantage. Disadvantages: first, it's a bit more complex. The code for it to do this is a bit more complex than the other option, and it's relatively slow. That is to say, the theoretical speed limit is lower for this than for the other. It's used in, as I said, the Texas Instruments operating system, but also in Michael Vincent's Tachyon link and in my Bell routines. Okay, so the second way to send over a byte is very different from the first. You use the tip of the link cable as a clock, and the clock indicates when the ring should be read, and the ring is what contains the actual data. Now, in this case, I've chosen to read the ring each time the clock changes. Now in this case, I've chosen to read the ring each time the clock changes. So if the clock changes from high to low, I read the value. If the clock changes from low to high, I read the value again. You can make other choices on that. So here we have a changing clock, and the corresponding value is low. So because it's low, it's a 0. And here we have another changing clock. So the corresponding value here is high. So it's a 1. Same thing goes here. A high line means a 1. And so this way you can transfer data as well. Now this has the advantage that 2 advantages, in fact. The first being that it's a bit faster in theoretically speaking, it's a bit faster. And the second is that it allows for more than 2 calculators to be linked. Because in the first way that I showed you, for every bit that you send, the receiving calculator has to acknowledge. But what are you going to do if there's more than 1 calculator receiving at the same time? They cannot all acknowledge the bits, because that just gives a lot of chaos. But this way you can send a message to more than 1 calculator, because the sender just sends and the listeners do nothing but listening. All they do is see when does the clock change, and when the clock changes they pick a value from the ring. So that's an advantage, big advantage. A disadvantage is that the timing makes it more complex, because different calculators run at different speeds depending on your crystals, depending on your batteries, depending on your model. You cannot reliably use timing, and the data, or the clock, sorry, on the tip line tries to help overcome that problem, but there's still delays involved. The delay between when you detect that the tip has changed and the time when you read the ring, for example, is not the same on all calculators. So finding that sweet spot of sending as much bits as you can in the shortest amount of time and not losing bits is very small. And you could use checksums, parity bits for that to make it recover from errors, but that's quite complex. This is used in my Collapse project, and also I think in the CalcNet by Kerm Martain, I think his name is, I'm not entirely sure. Right, so the 2 projects that I've worked on are the Bell project and the Clap project. The Bell project is for 2 calculators to link, and the Clap project is for networks of calculators to link. I'd like to walk you through both send and receive routines, so you can get an idea of what the differences are and how to use this in your code. I already opened the bell library before, so I'm going to continue on that. This is the bell send routine. First of all, you need to store your byte because you're going to lose it in A. Then you set both lines high just to make sure that everything's alright, and you use a bit mask. Now, what is a bit mask? To have a very, very short explanation of a bit mask is a byte with one bit being 1 and the others are 0. And the bit that is 1 can be used to indicate which bit you want to read from another byte. Right, so how does it work? Let's say this is your data and this is your bit mask. So it's a byte with 1, 1, somewhere in the middle or the beginning or the start, you don't know that. Now that acts as a mask, obviously, to the data. So if we overlay this, you can read 1 bit at a time. Okay, this is a very childish explanation, but I hope it's enough to give you a feeling of how it works. Maybe I'll have to do that again, but we'll see. So what we're going to do is use this mask that I showed you to pull out one bit, the first bit, and send it, and then pull out the second bit and send it, pull out the third bit and send it. So first you AND your current value, which is A, the byte that you want to send, with your bit mask, which is E, which results in a Z flag, 0 flag being set or reset depending on the value of that bit in that place in A. And then the routine jumps to either please do a 0 bit or please do a 1 bit. Now, the 1 bit pulls low the ring. This is the first method that I showed you before, not the second, mind that. So it pulls low the ring, and then it waits and reads the tip patiently for a while until it times out, or until the tip is being pulled low by the other calculator to acknowledge that it received a 1. And when that happens, it sets both lines high again, and again it starts to wait here, reading the tip to wait for the other calculator to release it, and then it's done and it goes on to the next. Yeah, next bit, that's it. If it's a 0 bit that you want to send, the thing is exactly the same on the other way around. So first you pull out the tip, then you read the ring, not the tip, and then down here you set both lines back to high as soon as you've received the corresponding ring going low, and you wait for that ring to go high again, and then you go to the next bit. Then we rotate the mask, and if the resulting value is 0, then we're done. So that's how the bell library does it. That's the serial way. So each bit is being acknowledged by the receiver. Right, so now let's take a look at the other version, the other way to do it, the clocked version. The Calculator Link Alternative Protocol, or the CLAP project that I worked on, uses that method because obviously it has to communicate with more than one other calculator. So if you go to clap.tremendous.com, and then you go to software, clap library, and then assembler library, then you get a zip file, and in that zip file you see 4 include files. Now these 4 include files are very much structured in the way that I explained the calculator networking stack. So there's a low level that contains all the stuff you need to read and set lines. There's a medium level that does the byte work, high level that does the string and block work, and then there's a network layer include file. So we're working on the medium level right now, and we're going to take a look at send byte. So send byte again uses a bit mask, works a bit different from the other bit mask, but the principle is the same. It saves our byte for later recall, then it sets both lines high just in case, again all the same. Then the send loop is different. We take our value, our data that we want to send, we AND it with a bit mask, and if it's 0, then we send a 0 bit, otherwise we send a 1 bit. So what we do here is we pull low the ring to signify that we want to send a 1, and here we set the ring high to signify that we want to send a 0. Either way, then we toggle the tip line, and we wait for a while, and we toggle it back, and wait again for a while, and we're pretty much done. All we have to do then is rotate the bit mask that we're working with, see if we're done yet, and if not, we go back to send loop. So we do the next bit. So that's a much simpler routine. It's faster, it's simpler, it's easier to maintain. But as I said, it does not acknowledge the bits. So if you want to acknowledge the bits, or if you want to use a parity check, you have to build that in yourself. So that's the sending part. Now the receiving part. Let's first go back to the bell include file, where here we have our receive function. Am I in the right place? Yes, receive byte. Now first again we set both lines high just in case, and then the rest of this function is pretty much the same as the send function, because obviously it also does pretty much the same thing. It's pulling a line low, and then it's waiting for something, and it is releasing it again, and it is waiting again, and pulling the other line low. So the basic thing that it's doing is very much the same, only the order in which it's doing it is different. So if we look at the code, you see the same thing. We have a bit mask here too. We load the byte here as well, and then we read the lines, and if one of the lines changes, either the tip or the ring, then we jump to the bit of code that is responsible for that stuff. So ring low here, tip low there. So if the ring is low, then we set the tip low as well. Okay, so here's a pop question. Why am I setting low high here and not low low? Because we just saw that ring is low and we want to set a tip low. So both are low, right? But if you want to be able to check afterwards if the other calculator has released the ring, then we cannot be the one pulling it low as well. Because if one calculator pulls it low, all calculators will read it as low, including our own calculator. So pull the tip low, but leave the ring high. Now we know that the other calculator is pulling it low, but that doesn't change the fact that if it releases it, it will go up high again. So back to the code. So we find ourselves in the situation that we can store a 1 bit here, because the ring has been pulled low. So we acknowledge it, we store the bit, and then we wait for the tip to be released. And as soon as the tip is released, here we do that. And as the ring is to be released, and if the ring is being released, then we jump to next bit, otherwise we time out. And the same thing, if the tip is being pulled low, we pull down only the ring, and we wait for the tip to be released. We do nothing, of course, because the bit is 0. And if the tip is released, we go to next bit, and otherwise we time out. And next bit resets both lines, rotates the bit mask, and if it's done, it returns. And that's it. So it's very, very similar to the send routine. Only the order of things is a bit different, and of course you're storing things in A instead of sending out A. But the basic structure is the same. Now the other way of doing it, the clap way of doing it, there is a big difference between sending and receiving. I'll show you. So let's go back to the clap file, the mid-level include file. If you're reading a byte, what we do is we have a bit mask, and we have some byte that we're going to store it in, and also we have a timeout. Now this version has another feature, and that is that you can disable the timeout, and if you disable the timeout, it will return when you press clear instead of when the timeout is hit. So again, we call high just to make sure that we're not doing anything stupid, and then here's the code that does the checking for clear to be exit, and this is the important bit. If the tip has been pulled low, then we go on, and otherwise we jump back into the loop. So the tip has been pulled low, we read the ring, and depending on the ring, we either set this bit using the mask, or we don't. And in either case, we rotate the mask, and then we wait for the tip to be released by the sender. And then we're done. Oh, well, perhaps we're done. We're done if the mask is 0, and otherwise we do the next bit. I think you understand my point. So that's it. Go to the Clap website or the Bell website, download the libraries, and feel free to use them as much as you like. Also, I'd really appreciate it if you like the tutorials, if you think they're useful, if you really think you could use some pointers in some specific area, please leave a comment and I'll try to get back to them. Thank you, and see you next time.